All right, today we're jumping into electrostatic potential. Now, I know that sounds a little intimidating, but trust me, it's not. The best way to think about it is like an energy map for the space all around electric charges. We're going to figure out exactly how this map gets drawn, and more importantly, why it's the secret behind everything from a bolt of lightning to the battery that's powering your device right now. So let's start with a big question. What does it even mean for a point in empty space to have energy? Well, let's think about something we all know, gravity. Imagine holding a bowling ball way up in the air. That ball has gravitational potential energy, right? The higher you lift it, the more work you did, and the more energy it has stored. An electric field works in a really similar way. It creates its own kind of energy landscape, but instead of acting on bowling balls, it acts on electric charges. So here's our game plan. We'll start with how energy works in an electric field. Then we'll define exactly what potential difference is. After that, we'll get our hands dirty and figure out the formula for a simple point charge. We'll even work through an example with real numbers, and then we'll wrap it all up with a quick summary. Let's dive in. Okay, section 1, energy in an electric field. Remember that bowling ball? You have to do work. You have to burn some energy to lift it against gravity. Well, it's the exact same idea here. To push an electric charge against the force of an electric field, you have to do work. And that work doesn't just disappear, it gets stored up as potential energy. And this picture shows that idea in action. So imagine there are some big charges somewhere creating an electric field. Now we bring in our own little test charge, that's the little q, and we want to move it from point R over to point P. If we're moving it against the field's natural push or pull, some external force has to do work to make that happen. And that brings us to a super important definition, potential difference. As you can see from the formula, it's simply the work it took to move our charge from R to P, but then we divide it by the size of the charge, Q. Now, why do we do that? It's a clever move because it makes this measurement about the field itself, not about the specific charge we happen to be moving. It becomes the work done per unit of charge. It's a universal property of that energy landscape. And this quote from the source material just nails it. The potential difference isn't really about our little test charge. No, it's a fundamental characteristic of the electric field that was already there. It's a number that tells you about the energy difference between point R and point P, period. Okay, so we can talk about the potential difference between 2 points, but what if you want to know the potential at just one single point? How do you do that? Well, physicists came up with a really smart convention. We all just agree on a universal starting point, a reference. We say that a point that's infinitely far away from any charges has a potential of 0. Think of it like sea level for energy. Now we can measure the altitude or potential of any other single point relative to that 0. So how do we actually calculate this potential? Let's start with the absolute simplest case you can imagine, the potential created by a single, solitary point charge. We're about to build one of the most important formulas in all of electrostatics. This image sets up our mission perfectly. We've got our source charge, the big Q, sitting at the center, and our goal is to find the potential at point P, which is a distance r away. Using our sea level rule, we're going to calculate the total work it takes to drag a tiny test charge all the way from infinity up to that exact spot. Now, the full math involves some calculus, but don't worry, the logic is actually really straightforward. Here's how it works. First, you figure out the force on your test charge at any given spot. Then, you calculate the tiny bit of work it takes to move it a tiny distance. Step 3 is where the magic of calculus comes in. It adds up all those infinite little bits of work over the entire journey from infinity. And finally, you just divide that total work by the charge, and boom, you've got the potential. And after all that, we get this absolutely beautiful and simple formula. The potential V at a distance r from a charge Q is just Q divided by 4 pi epsilon naught r. That epsilon naught thing, it's just a fundamental constant of the universe, nothing to worry about. This elegant little equation is a real cornerstone of physics. And this graph is awesome because it shows a really important difference. Look at the black line. That's the electric field. It drops off super fast as you move away because it's proportional to 1 over r squared. But look at the blue line. That's our potential. It's only proportional to 1 over r. So the potential fades away much more slowly with distance than the electric field does. Okay, theory is great and all, but let's make this real. Let's plug some actual numbers into the formula we just built and solve a problem. All right, Here's the challenge. We've got a charge of 4 times 10 to the minus 7 coulombs, and we need to find the electric potential at a point that's exactly 9 centimeters away from it. Okay, first things first, let's get our data organized. Our charge, Q, is 4 times 10 to the minus 7 coulombs. The distance, r, is 9 centimeters. And this is super important. We have to convert that to meters, so it's 0.09 meters. And that whole constant, 1 over 4 pi epsilon naught, it has a nice, neat value of 9 times 10 to the 9.
So we just take our values and plug them straight into the formula. It's the constant times the charge Q, all divided by the distance r. You run the numbers, and what do you get? 4 times 10 to the 4 volts. That's 40,000 volts. Pretty significant.
Now here's where knowing the potential becomes a real superpower. The example then asks, okay, how much work would it take to bring a different charge, a new one, to this same spot? Well, because we already calculated the potential of the spot itself, the problem is incredibly easy. The work is just that new charge, Q, multiplied by the potential, V. And that gives us 8 times 10 to the minus 5 joules. Way easier, right? Whew, we have covered a ton of ground. So let's take a second to pause and put all the most important pieces together in one handy toolkit. If you take anything away from this, it's these 3 ideas. First, potential difference is just the work per unit charge to go between 2 points. Second, the absolute potential at a single point is the work per unit charge to get there from infinity. And third, our master formula for a point charge gives us potential at any distance r. These are the core tools of electrostatic potential. So when you zoom out, what's the big picture? This energy map we call potential. It isn't just some abstract number in a physics textbook. It is, and this is not an exaggeration, the very foundation of our modern technological world. That potential difference between the two ends of a battery, that's what shoves electrons through circuits and brings every single one of our devices to life. Which leaves us with one final, fascinating thought. How does this simple, elegant map of energy and space scale up to power the incredible complexity of the world all around us?